All right. Hello, everyone, and thanks so much for clicking on this link to this video of this research talk that I'm recording. So this is actually a research talk that I've given twice already. Once when I was visiting Professor Vera Dumberg's group at Saarland University, and a second time when I was visiting Professor Heinrich Schütz's group at LMU in Munich. I gave very similar versions of the talk I'm about to record uh, at both of those places, and it was essentially in the context of advertising our ACL 2025 work, ACL 2025, which was in Vienna. So because I was, in the neighborhood, it was my great honor and my great pleasure to give this talk. Unfortunately, I didn't record it, which is why I'm redoing it now. So hopefully you're excited because today I'll be talking about capturing intentions within figurative language. So given the title of this research talk, I think a very nice place, a natural place to start is to talk about intentions. So intentions are a fairly important and powerful concept in, excuse me, natural language processing and in computational linguistics. For one, intentions are these things that guide how we communicate, right? So whenever a speaker produces an utterance, you're almost guaranteed that there was some kind of intention or intended meaning behind that utterance. And so modeling or knowing the intended meaning behind an utterance is very important when we're trying to understand and generate language in computational linguistics and NLP. And intentions are these things that have very interesting properties. For one, intentions can be concealed, right? So when someone lies, and they can also be exposed, right? When a journalist finds out that someone is lying, for example. Intentions also have another very interesting property, which is that even though they're directly related to language and to what we say and how we communicate, they don't necessarily depend on the knowledge of that language. So what do I mean by this? Essentially, one can communicate their intentions without a listener actually needing to understand the words being used to communicate those intentions. So a good example of this is illustrated in this picture here. So essentially, this is me and some of the fine folks that I met and also sort of rekindle with at ACL 2025 in Vienna. So this was sort of a group dinner with all these fine folks. And, we were having this dinner. It was great fun. At some point, I got up, right? I got up and I heard behind me someone say something. And of course, because we were in Austria, they said that's something in German, quite naturally. I don't speak German, and so I didn't understand any of the words that were spoken ostensibly to me, right? And so I turn around and I see that a server is saying something, um, and I don't know what, but because of sort of the context and because I was sort of clearly in the way of the server and because the server looked annoyed, so because of the context, I was able to infer that the server's intended meaning was to tell me, hey, guy with the nice hat, please get out of my way so I can do my job, right? And so that's another interesting thing about intentions is that they can be understood and communicated without any linguistic knowledge of the language being used to communicate them. And finally, if we tie this a bit more to NLP and to computational linguistics, intentions can be ascribed to systems which may or may not understand, right? And so this has been famously or maybe infamously reported in articles like this one from the New York Times. Okay, and so intentions are clearly this very important concept that we ought to care about as language researchers. So the question that naturally arises is, can LLMs interpret the intentions of their users, right? So LLMs are, at least at the time of this recording, the sort of technology, language technology of choice for designing any kind of system, right? Whether it be a translation system or a dialogue system. If you want something that's sort of state of the art, then you almost always, or I want to hedge this a little bit, but you sort of, in many cases, want to use an LLM, right? So in that case, because these systems, these technologies underlie most user interfacing language systems, we then sort of want to naturally ask, well, do they understand the intentions of their users? Are they able to sort of do this the same way that humans, or maybe not the same way, but can they do it like humans, right? So there have been many studies that have looked at this question. So there's been many that have used sort of what are called these pragmatic benchmarking or benchmarks, where essentially you have some kind of utterance, and the task is for the LLM to determine the intended meaning of that utterance. So this has been done on implicature and presupposition and many other pragmatic tasks. And what's been shown is that there's this sort of scaling law trend, where as the models get bigger and more modern, then they're better able at inferring the intended meaning. The one caveat with that finding, though, is that these sort of results have all been sort of confirmed on literal language phenomena. So whenever a speaker is sort of using language literally. On the other hand, when it comes to non-literal language like irony or hyperbole or metaphor, other studies have, including our own, have shown that LLMs struggle to capture the intentions when a user is using non-literal rather than literal language, right? So to describe a thunderstorm as amazing rather than actually terrible, an LLM gets a bit tripped up there and sort of tends to interpret things a bit too literally. So to illustrate this point a bit better, let's look at an example, right? So this is an example that we tested in our paper, but that's also been tested previously in other papers about the competence of LLMs when it comes to capturing the intended meaning of users. So in this example, John is a teacher, and he's talking to the principal of the school that he works at about a student who didn't do very well on an entrance exam. And so John, to describe this student, says, "This one is really sharp." And so what could John have meant by this utterance? So we have a list of four possible intended meanings, and given the context and the fact that the student didn't do very well on the entrance exam, it's likely that John is being ironic or sarcastic. And so what he's trying to say, despite the fact that literally this might mean that the student is smart, what John is probably intending to say is that the student is not very clever, right? So this is sort of I think, the prototypical or sort of the quote unquote correct interpretation of this utterance. Well, how does an LLM sort of interpret this utterance? Well, if you give this scenario and these lists of meanings to an LLM, either big or small, um, both sort of tend to interpret utterances literally. So in this case, places most, if not all, of the weight on the literal interpretation. And like I just said, this has been tested by us on both small and large models. But it was originally sort of presented as an empirical result in this paper. And so the question which I'll try to answer in the remaining part of this talk is, this is a problem, right? If you want an LLM to underlie most user-facing technologies, then they ought to understand the intentions of users even when they use figurative language. So the question is, if they can't, well, how do we make them sort of do so, right? How do we enable them to interpret intentions in figurative language, right? So this will be the question that I'll be trying to answer in the remainder of this talk. I'll start by giving a bit of background and related work. So I'll talk about how we might capture intentions intuitively by talking about work by Grice, where he introduced the cooperative principle. I'll then talk about the sort of most widely known um, implementation of Grice's intuition, the rational speech act framework, which is essentially this computational model of intentions, but which I'll argue only really works for literal language. And so that will be a nice segue for me to introduce the work that we presented at ACL, RSA square, which is a generalization of the RSA framework, which I'll argue is able to capture or to model the capturing of intentions of utterances, even when they're used sort of figuratively or non-literally. So that's the general outline for the remainder of this talk. Okay, so how might we start to think about capturing intentions when it comes to figurative language? So to think about this question, I'd like to first start by talking a little bit about Grice and his seminal work, Logic and Conversation. So in this work, Grice essentially framed communication as a game of cooperation between listeners and speakers. And in this way, modeled sort of intuitively capturing intentions in communication. So what do I mean by this? Let's illustrate this with a few examples. If, for instance, you have the utterance, I like that blue object in the context of a reference game, so you can either refer to the blue square, the blue circle, or the green square, then the meaning here, the intention of the utterance is which of these three objects was the speaker trying to refer to? Well, if we think of the listener and the speaker in this kind of cooperative game where they're trying to help each other out, what the listener will do here when trying to interpret the intention of the speaker that produced this utterance is they will say, I know that blue is sort of literally ambiguous. It could be the blue square or the blue circle. But I also know that the speaker is trying to be as cooperative as they can. So if they wanted to say the blue circle, then they could have just said circle and I would have gotten it instantly. Instead, they chose to say blue, which leads me to believe that it couldn't have been the blue circle, but it's probably the blue square, right? So this is one example where you might reason about speakers and listeners kind of recursively to uh, identify the most likely intended meaning of an utterance. You can also do this in the context of a figurative utterance. For instance, during a thunderstorm, a speaker says something like, wow, the weather is amazing. So the listener will sort of observe this utterance, observe the context of the weather, and see that there's sort of incongruity or contradiction between the two. The listener will then say, well, there must be a reason for why the speaker said this contradiction because I know they want to be somehow cooperative. So what the reason is that, oh, the speaker must have been sarcastic or ironic, and sort of that's how they sort of resolve this conflict, and that's how they sort of would most likely interpret that utterance to mean the weather is actually terrible and the speaker is annoyed about this. So this is great intuition, but how do we actually implement this? So there have been many attempts to implement this computationally. I would say the most famous and widely known implementation is the RSA framework. So in the RSA framework, communication is still modeled with this idea of speakers and listeners, but now the speakers and listeners are instantiated as probabilistic agents, which reason about each other recursively through a sort of recursive reasoning algorithm. So what we'll do now is we'll first discuss the vanilla or standard RSA framework. First, its high-level intuitions, then more concretely, its equations, and then finally, its applications to capturing intentions in the context of literal language. And then I'll contrast this with the RSA square framework, which, like I said in the sort of introduction, is this generalization of the RSA framework, which I'll argue is able to sort of do the same but for figurative language, which is something that we'll see that the RSA framework cannot do. Okay, so what is firstly, the intuition behind how the RSA framework works? So let's use this same example of I like that blue object in the context of referring to the blue square. How does the RSA framework, firstly, intuitively explain the fact that this utterance is most likely to be referring to the blue square? Well, to do this, what the RSA framework does is that it sets up a space of possible intended or inferable meanings, right? So in this case, it's quite naturally the list of three objects that can be referred to. And then what the RSA framework does is that it introduces, firstly, a literal listener. So a listener which interprets utterances completely literally. So in terms of more probabilistic equations, the literal listener is a conditional distribution over these meanings given the context and the utterance. So the context here is the list of possible referents or objects that can be referred to, and the utterance is I like that blue object, right? And the literal listener, what um, it does is it places probability mass on all of the objects which are literally compatible with the utterance. So the blue square is compatible with I like that blue object, so is the blue circle, but the green square is not. And so we have a uniform distribution between these two meanings. So that's the sort of base case, because what you're going to see is that the RSA sort of uses recursion to create more and more pragmatically or context or really intention aware interpretations of utterances. So it does this recursively, and you can just think of the literal listener as this kind of base case of conditional probability on the meaning space. Then what happens is that the RSA framework introduces additional levels of reasoning. So it introduces the pragmatic speaker, which reasons about the literal listener, and then the pragmatic listener, which reasons about the pragmatic speaker. And in the end, the final result is the pragmatic listener, which thinks about the pragmatic speaker, about their sort of conditional likelihood of generating a blue or circle or green or any other single word adjective to describe the target, and sort of decides, well, it's more likely that the speaker, the pragmatic speaker, decided to say, I like that blue object because they wanted to refer to the blue square rather than the blue circle. And so because of this reasoning, what the pragmatic listener will end up doing is it will upweigh, the meaning or the object, which is more in line with what we think are the actual intentions being communicated, and it will downweigh, in this case, the meaning, the blue circle. Right? So this is intuitively how things happen. So they go from sort of a literal interpretation to a more pragmatic one. So here, pragmatic, you can just think about it as using the context to better understand the intention, or sort of something that is trying to capture intentions more than just a literal listener. Now, what are the actual equations behind this intuition? So if we look at the literal listener, as I just said, is a conditional distribution over possible referable meanings given the context and the utterance. But how is this conditional distribution actually computed? Well, essentially, you can imagine that you have some kind of prior probability of referring to each of the objects, and then that prior gets blocked or gets unblocked based on whether or not each object is compatible with the utterance literally. So you take the prior, and then using this indicator function, you either block or unblock the prior based on whether the meaning, so the thing in the sort of target part of the conditional distribution, is compatible with the utterance, in this case, blue, right? So in that case, the blue square and the blue circle are compatible with the utterance, but the green square is not. And so if you had initially a uniform prior distribution over the three objects, then it gets blocked on the green square, and then it gets sort of redistributed to the blue square and the blue circle. And that's how the literal listener is defined. What about the pragmatic speaker? So the way the pragmatic speaker is defined is using a conditional distribution again, but now over possible utterances available to the speaker, given the context, the same context as the literal listener, and a meaning that they want to convey, right? And so how do we induce this distribution for a speaker given a context and a meaning that they want to convey? To do this, we sort of think of, or RSA thinks of, how can the speaker be maximally informative? So to sort of define this more formally, RSA uses these ideas from information theory to define information, where the log of the conditional distribution of the literal listener is the sort of information being conveyed or communicated by the pragmatic speaker. And so the pragmatic speaker wants to sort of maximize this, but they don't want to do this at any cost, right? So they would like to keep their utterance brief and relatively short, and so that's why there's also a penalty term. So this is the sort of utility function of the speaker, the sort of idealized function that the speaker uses to decide how useful an utterance is. So what is done is this function is taken and then placed in a softmaxed distribution, right, where alpha is just a temperature term. And then this just gets converted because you have an exp and a log to this equation. So then this is the equation for the pragmatic speaker. Finally, for the pragmatic listener, how do we get this sort of redistribution of probability mass towards an intended meaning that is more pragmatic or more aligned with sort of human interpretable or human compatible intentions? So to do this, RSA uses Bayes' rule, which, as a reminder, is this conditional likelihood times this prior probability. So the posterior is the same sort of type as the literal listener conditional distribution. So it's the meaning given the context and the utterance. But this time, the prior is reweighed by how likely the speaker is to use each utterance to refer to the meaning in the sort of target here. So what the what the pragmatic listener will do is they'll reason explicitly about the speaker with Bayes' rule, and this will cause probability to redistribute towards the more informative meaning. And so this is these are the equations underlying the sort of standard RSA framework. And it's fairly important for me to actually present these equations in full because we'll then be able to contrast them with the RSA square equations. But turning back to the RSA equations, the RSA equations and sort of its intuitions have been used in several cases to capture the intentions of users in the context of NLP. So in particular, RSA has been used in several studies. This is just one of them for informative image caption generation. And it's also been used for evaluation. So how can we evaluate some generated text? Well, we can imagine some listener and how likely they are to interpret the text as the speaker intended them to interpret it. But mostly RSA has been used for pragmatically informative generation, right? So creating texts which are more informative, which are more easy for a listener to identify the intended meaning. So it's been used for summarization, for query focused summarization in our workshop paper and featured at EMNLP 2024. But also for controllable text generation and code generation. So these are two nice studies published or brought to you by the group at the Saarland University in Vera Dumberg's group. So the RSA framework has been quite useful and practical for capturing intentions, but all of this sort of space is in the context of literal language, right? So in the context of using language literally to communicate one's intentions. So what about figurative language, right? What about using irony to describe a thunderstorm, right? So using something like, wow, the weather is amazing to imply that the weather is in fact terrible. So if we use the same kind of setup, the same equations, but now the meaning space is in this case weather states, how does the RSA framework explain that wow, the weather is amazing should be interpreted as the weather is in fact terrible? Well, it runs into problems basically. Because firstly, for the pragmatic listener to provide probability mass over meanings, the literal listener has to do so, right? And so, okay, how do we compute the conditional distribution for the literal listener? Well, we have to evaluate this indicator function, right? Let's suppose that the prior is uniform. Well, this indicator function is only going to fire for literally compatible meanings with the utterance while the weather is amazing. So in this case, probably just this weather state. But then what happens for the terrible weather state, this weather state here? Well, it doesn't belong to this set, so the indicator function does not fire. So then the conditional probability here is 0 for this terrible weather state. And so this 0 propagates here and then here. And so then the pragmatic um, conditional distribution for the terrible weather state remains 0, which is definitely a problem because it doesn't actually align with how humans might interpret this utterance. So this is definitely a problem. And one of the reasons why we can't just stop here and say, well, RSA plus LLMs, that should be the solution to fixing LLMs troubles when it comes to interpreting the intentions of their users um, in the context of figurative language. Because remember, that's the goal we're trying to go towards. So we're definitely not the first people to notice that this is a problem in the RSA framework. In particular, in 2014, Cao and colleagues noticed that this was a problem inherent with the standard RSA framework and proposed a fix. The fix relied on introducing an affect random variable, hence the name affect-aware RSA. So an affect-aware RSA, the use of this affect variable is what enables non-literal interpretations of utterances. So for instance, in this context of a thunderstorm, what affect-aware RSA does is it says this context is typically associated with negative affects, like joy, like annoyance or frustration or sadness. And those negative affects are typically associated with bad weather, right? So you can see how there's like a sort of jump through this affect random variable to get to a non-literal interpretation. And affect or RSA has been shown to work, right? It's been shown in many studies to be predictive of human non-literal interpretations of utterances, which are meant to be interpreted non-literally. But it has to do this through, like I said, this indirect modeling of affect, which is not a very sort of generalizable, scalable way of doing things. So for instance, if we think back to the motivating example I gave at the very beginning, where I sort of showed that LLMs are prone to interpreting literally, then, you know, in this example where John is talking ironically about a student, maybe John is being humorous, or you know, some kind of affect can be used to explain John's behavior. Or maybe John is a very ironic person. John likes to be sarcastic or ironic all the time. Or maybe in this school, that's how you talk about students who don't do very well. You always talk about them sarcastically, right? It's plausible. I mean, it's a bit weird, but definitely plausible. Or maybe John is just trying to get the attention of the principal. He didn't really mean um, to convey any kind of affect. He just wanted to use the sort of non-literal utterance to see if the principal was paying attention. And so that's one of the reasons why affect is not always the solution in terms of explaining non-literal utterances. And also, if you think about trying to use this for LLMs, it's not a super scalable approach, right? Because for each sort of conversational context, you have to think of what are the relevant affects that might be able to explain some non-literal interpretation of the utterance. So that's a fairly difficult thing to do. Whereas in the method that we introduce in RSA square, we sort of try to model this directly, model this effect directly. So how do we do this? Well, I'll first start by giving you a bit of the intuition behind the RSA square framework. So in the RSA square framework, essentially what we say is that figurative language follows some kinds of systematic patterns. So irony, hyperbole, understatement, and so on, which we call rhetorical strategies. So for each rhetorical strategy, we can sort of find the intuitive systematic pattern and then operationalize it. And that operationalization can be introduced or integrated within the RSA framework to create a non-literal interpretation. So what do we mean though by systematic patterns? Well, for instance, when it comes to irony, that's when the intended meaning is the opposite of its literal meaning, right? Hyperbole, that's when an utterance overstates its literal meaning. And similarly, understatement, that's when an utterance understates its literal meaning. So all of these patterns we noticed could be directly operationalized and integrated within the RSA equations as you'll see a rhetorical strategy random variable. So what does this look like at a high level? So you can imagine again the utterance, wow, the weather is amazing, uttered in the context of a thunderstorm. And now you can imagine that we're going to use different rhetorical strategies to interpret this utterance. So we might use a literal rhetorical strategy, right? In that case, we just get the standard RSA interpretation of this utterance. But then what we do is we introduce these other rhetorical strategies, like irony. So in the case of irony, you might have the interpretation is flipped from the literal interpretation, right? So you have this ironic listener. You can imagine this is like a listener that always interprets utterances literally, or ironically, excuse me. And then similarly for hyperbole, you might have a hyperbolic listener. So a listener which always thinks you're exaggerating, right? And so because while the weather is amazing seems like an exaggeration to this listener, they'll place the probability mass one grade lower than the literal listener. And now what we have, right, is we have different interpretations of the utterances based on each rhetorical strategy. And actually what's going to happen is for each rhetorical strategy, we're going to have the RSA equations, which lead to some pragmatic interpretation of the utterance, but within the context of that rhetorical strategy. Okay, so now we have these different distributions over meanings. How do we recover a single distribution, right? Because that's kind of what we need for a comparison with a potentially human distribution. Well, we simply introduce a new marginalization, right? Where we use the probability of each rhetorical strategy. So we have to introduce a new conditional probability. And we use that to marginalize across all of the pragmatic conditional distributions conditioned on this extra rhetorical strategy random variable. So if you marginalize this, and if this probability is fairly well calibrated, we'll see how to do that in a second with the experiments, then what you get is something much more plausible, right? Where most of the probability mass is on the terrible weather state interpretation. Okay, so that's how this happens at a high level. Now, what about the RSA square equations? So here's a reminder of the RSA equations. Now, the way in which we modify the RSA equations to get the RSA square equations is firstly by introducing this rhetorical strategy random variable. With the rhetorical strategy random variable, what we do is we introduce a rhetorical function. So the rhetorical function is a generalization of the indicator function, right? So before we have this indicator function, which only fires if this meaning here is literally compatible with the literal interpretation of the utterance. But now that we have a rhetorical strategy, we can say, based on the rhetorical strategy, we'll have different types of indicator functions, basically. Or they don't even have to be just indicator functions. In this case, the rhetorical function is any function to 0, 1, right? And that enables us to, for instance, provide a non-zero um, mass to interpretations like the terrible weather state for the ironic rhetorical strategy and the, good but not amazing weather state for the hyperbolic rhetorical strategy. Okay, and so this rhetorical strategy random variable is introduced as a conditional random variable in this distribution, and that's used to index into the correct rhetorical function. We similarly have to introduce this rhetorical conditional random variable in the S1 and L1 equations. And then finally, because this causes us to create several different pragmatic listeners, one for each rhetorical strategy, then we have to introduce a marginalization equation. But altogether, this is the RSA square framework, and these are its equations, right? So now that we've presented the RSA square framework, the claim that I'll be making in the remainder of this presentation is that RSA square can capture the intentions of figurative language, so not just of literal language, both in principle and also in practice. And so to show this in principle, we'll look at how RSA square can induce human compatible interpretations of figurative language on a few toy data sets. And then we'll also see how RSA square can be used to mitigate the biases that LLMs seem to have, as evidenced in the sort of motivating example at the beginning, toward interpreting too literally, right? So this will hopefully convince you that RSA square can be used both in principle and practice to enable non-literal interpretations of figurative language. Okay, so let's look at some experimental setups and results. So for the sort of in principle claim that I'm making, that RSA square can induce human compatible interpretations of figurative language, the way that we test this is on two scenarios, which are toy, but are still scenarios nonetheless. The first one are scenarios that look like non-literal number expressions, so the use of hyperbole to describe the price of a kettle. And the second types of scenarios are ironic weather utterances, like the one that I showed in the example, in the running example for RSA square. So how do we set this up? For the non-literal number expressions data set, the task is essentially given some non-literal number expression, like this kettle costs $1,001. The expected output is some human compatible distribution over possible prices. So, we give this utterance to a human, we give them possible prices, we induce distribution with humans, and then we do the same thing with RSA square and affect-aware RSA as a baseline. And what we'd like to have as an output is a distribution as close as possible to the human distribution. So the experimental setup, a bit more formally, is utterances of the form the object costs some amount of dollars, where the object is either a kettle, a laptop, a watch. The prices range from 50 to 10,001. And in this case, the set of rhetorical strategies we consider include the literal hyperbolic understatement and halo rhetorical strategy. This last one is essentially when someone uses an exact number rather than a round number. So these were essentially decided just because of what the utterance and the meaning space look like. So you can't always do this. This is why I'm saying that this is a bit of a toy setting. But it's more of a proof of concept to show that in principle, we can induce human-like meaning distributions. And the other thing is, how do we actually elicit these probabilities? So we have some prior probabilities here, also a sort of conditional probability here. How do we actually implement these or compute these as part of the RSA square equations? So we, in this case, use human elicited probabilities for the prior and then uniform probabilities for this other utterance prior and the conditional distribution here. To be honest, the uniform probability distributions are not ideal. They're to be avoided um, if you can. So in another experiment, we have this being sort of human induced, and then you'll see that for the LLM experiment, this is LLM induced. But just for simplicity, in this setting, we just said let's just keep it uniform. And then how do we actually compute the rhetorical strategy function? That's another part of the RSA square framework, a crucial part. So we do this sort of by intuitively transferring the intuitions of each rhetorical strategy to a more concrete function. So for instance, the hyperbolic rhetorical strategy, its corresponding rhetorical function will only return one if the utterance is an exaggeration of the actual price. So if the price in the utterance is greater than the actual price. It's the opposite, right, for understatement. And then the halo and literal rhetorical strategy are defined similarly. So now we have all the pieces needed to sort of induce distributions with RSA square. So what do the results look like? So if we look at the utterance, the kettle costs $1,001, and we plot the distributions of humans, of affect-aware RSA, and of RSA square on, for instance, different meanings. So let's look at this first meaning where you interpret this utterance as meaning that the kettle actually costs $50. Then we see that essentially the green and red bars, which are the RSA square listeners, are in this case closer to the human distribution. In some other cases, than affect-aware RSA. In some other cases, affect-aware RSA is slightly closer. But overall, the general trend that we see, one of the general trends that we see is that the RSA square listeners are fairly close to the human distribution. Another interesting thing that we see is that affect-aware RSA seems to overshoot or overemphasize the literal interpretation of utterances, whereas this is a bit more mitigated for RSA square. On the other hand, one of the problems with RSA square is in this setting is that it places a bit too much probability mass on the sort of tail ends of the meaning space. So in this case, it puts a bit too much weight on prices that are greater than the literal interpretation, albeit this is only for the literal listener, but still you would ideally like both listeners to be fairly close to the human distribution, where the pragmatic one should be a bit closer. But one of the main reasons for why, or the main reason for why this sort of tail behavior happens is because of the conditional rhetorical distribution we use in marginalization, which is uniform as a reminder. And so that's why it places a bit too much weight on the sort of incorrect interpretation, on the incorrect rhetorical interpretation. And so that sort of skews the distribution a little bit. But overall, we get some probability distributions which are pretty close to the human distributions. So we do the same, almost the same thing for the ironic weather utterance data set. So we have utterances like the weather is amazing. In this case, the humans are given a picture and they're asked, given 5 different weather states, terrible, good, okay, um, terrible, bad, okay, good, and amazing. What is the sort of distribution you place on each of those induced by humans? And so the idea is, can we get RSA squared to induce a distribution that's close to the human one? So again, as a baseline, we use affect-aware RSA. In this case, though, I'm not going to go into details, but we use a small neural network to implement the rhetorical function. And also in this case, for the conditional distribution of the rhetorical strategy, it's human-induced rather than uniform. So that actually helps a lot. So this is just the formal setting, but that helps a lot in terms of the performance and sort of trying to avoid this tail and behavior. So again, we have a similar result where the red and green bar are the closest in this case to the blue human distribution. And in this case, we have sort of we've been able to mitigate the tail probability mass effect. So there's not as much mass on the sort of tail distribution than there was before. And again, we see that one of the affect-aware RSA listeners over emphasizes or over weighs the importance of the literal interpretation of this utterance. So that's the sort of first set of findings, which hopefully have convinced you that in principle, we're able to induce human compatible distributions of non-literal language in the context of figurative language. Um, this is just a table that compares the distribution between humans and the RSA square and affect RSA listeners and computes the mean absolute difference between them. So overall, the results are that on the non-literal expression data set, we're quite close to affect-aware RSA, and on the ironic weather utterance data set, we're even a bit better than affect-aware RSA. So like I said, this hopefully confirms that we're able to induce human compatible interpretations of figurative language with RSA squared. Okay, now onto the in practice sort of claim that I made at the beginning, so that RSA squared can be used to mitigate the biases LLMs seem to have towards interpreting utterances too literally. So to test this, we integrate LLMs within the RSA square framework and the RSA framework as a baseline. And we evaluate this integration on the Prague Mega Plus dataset, which is a new irony understanding dataset that we developed for this study. So in this case, the inputs are conversational scenarios that look like this. You know, we have the context, the utterance, and then a list of meanings. And the expected output is some distribution over these meanings, where in this case, we don't have a human distribution, but we do have the sort of correct intended meaning labeled in the data set. And so the goal would be for the LLM RSA square adaptation to place as much probability mass as it can on the correct intended meaning. So before we get to the results, how do we actually integrate LLMs within the RSA and RSA square equations? So just a reminder, here are the RSA equations and the RSA square equations. The way that we integrate LLMs within these two sets of equations is kind of in a three-part step. The first thing that we do is we set the literal listener distribution to an LLM instruction-tuned distribution. So this is something that's been commonly done in other RSA plus LLM adaptations. And so we sort of use the same idea. Then we also use a base LLM to approximate the utterance prior here. And then finally, we use the same instruction-tuned LLM as the one to set the literal listener, but this time to induce a prior distribution and a rhetorical strategy distribution. So altogether, with these modifications, we get the LLM RSA and RSA square equations. And these equations are, like I said, applied on all of the scenarios in the Prague Mega Plus dataset. So the Prague Mega Plus dataset, we've already sort of been through this, but as a reminder, you have the sort of conversational context. So that's the context part in the conditional distribution. Then you have the utterance. The set of meanings are always sort of four meanings. One is a lexical overlap meaning, another one is a non sequitur, and then you have the literal and non-literal interpretations of the utterance. And in this data set, we consider two rhetorical strategies, the ironic and the literal rhetorical strategy. So for the literal listener, which is set to the LLMs, we explicitly tell the LLMs to interpret things either ironically or literally with a bit of prompt engineering. So that's why we actually also have a validation set in the PragMega Plus dataset, um, which is an expansion of the PragMega dataset that was originally introduced by Hu and colleagues in the 2023 ACL paper. But now if we apply the RSA square and RSA equations with the LLMs as the backbones to these scenarios, then we get probability distributions over these four types of meanings. And then we average those probability distributions across all of the scenarios. Um, so what are the results that we get? So we'll plot the distributions for the LLM RSA listeners as well as the LLM RSA square listeners. So for the non-literal meaning, so the sort of correct meaning interpretation of the utterance, it looks like introducing um, or combining LLMs and the RSA square framework together significantly helps, right? So compared to the LLM RSA baseline, the LLM RSA square baseline does much better, placing over 80% of the probability mass on the correct intended meaning. And also as a result, it sort of mitigates this bias that LLMs seem to have towards interpreting too literally. For the distractor meetings, the results are the same for the LMRSA and LMRSA square baseline, so it's just nice that there are no significant changes there. But overall, this is the general result. We seem to have sort of a mitigation of the biases that LLMs seem to have towards interpreting too literally when they're coupled with RSA square, but not when they're coupled with RSA. And just a reminder that the literal listener for the LLM RSA listener, that's actually just the distributions induced by the LLMs directly. And so it looks like if you just trust the LLM's judgment directly, it places 50% of the probability mass on the non-literal interpretation and 50% on the literal interpretation. So that's quite bad if all of these scenarios are supposed to be interpreted non-literally. Okay, so overall, the takeaways or the upshot from these experimental results are, firstly, I think in principle, we've shown that RSA squared can induce human-compatible interpretations of figurative language. So we've shown this on non-literal number expressions and also on ironic weather utterances. And we've also shown experimentally that RSA square can be used in practice to mitigate the biases that LLMs seem to have towards interpreting figurative, or in this case, ironic utterances too literally. So overall, in this talk, I explored the question of how to design language systems which capture intentions of users in the context specifically of figurative language. So I explored many answers, firstly intuitively from Grice, then computationally from the RSA and affect-aware RSA perspectives. And then I sort of introduced the RSA square framework as a more generalizable alternative to affect-aware RSA. And I showed that it can work in principle and in practice to unlock human-compatible non-literal interpretations of figurative language. And so we're pretty happy. So if I take a little break here, we're pretty happy with this work. We're excited because we think it's unlocked a few interesting future directions. So first of all, how can we use RSA square for something less clear cut, like idioms and metaphors? Like, what does the rhetorical function look like in that case? Some other questions that we've been thinking of is how do we integrate speech into RSA square? So the probability of the rhetorical strategy, that's probably very well approximated by using some kind of speech heuristic. So using tone of voice or pitch. Those are probably very discriminative features when it comes to determining the rhetorical strategy. And also, in all of these experiments, we've always assumed to know what the set of rhetorical strategies are. But I mean, in more realistic settings, maybe that's not the case, right? So maybe we'll want to be able to automatically induce the rhetorical strategies. So we have a clustering algorithm which tries to do that. It does not do very well. That's why it's in the appendix rather than in the main part of the paper. But we think that it might be an interesting venue for future work, and so we're happy to chat with anyone who might be interested in things like that. So I'd like to thank you for your attention. Thanks to the collaborators for their fantastic work on helping us get this paper submitted and published. And yeah, thanks again for listening.